Hello, everyone. Welcome to this week's Corona seminar. We have two talks today. Our first speaker is Janghoon, who is currently a third-year PhD student at the Chemical Engineering Department of Carnegie Mellon University. His supervisor is Professor Amir Bharati Farimani. Janghoon is currently advancing the field of computational catalysis and molecular design by leveraging machine learning. Janghoon, you may want to start the presentation. Thank you for joining us. We can't hear you.
Hear me?
Could you say that again? Sure.
Hello.
I think your voice is, the volume is pretty low.
Was it okay for people joining
I'm
this?
sorry, guys. Is it me or
We
problem
cannot
from
hear you.
Janghoon?
We
No,
cannot
we
hear
cannot
you.
hear.
Okay.
Uh,
Not, not good.
No, we cannot hear you.
Still?
Yeah, we heard still.
Okay, I will just take a read login.
No, it's much better. Yeah.
Now it's good. Now it's good.
Now it's good? Okay,
Yeah.
good. Great. Okay. Let me share my screen. Yeah, thanks for the great introduction. And yeah, I'm Janghoon, a PhD candidate in Chemical Engineering Department at Carnegie Mellon University. And I'm really thrilled to have this opportunity to present at the Crunch seminar today. Today, I will talk about the fascinating topic of catalyst property prediction using our innovative large language model, which we've named CatBERTa. Yeah, let's get started. Okay, I assume that many of today's audience may not be familiar with the concept of catalyst and chemical engineering. So I will briefly walk you through what catalysts are and why they are important in chemical engineering field. And catalyst is the substance that can enhance a chemical reaction. Catalysts typically consist of inorganic metal atoms. And in order for a reaction to proceed, the reactant must overcome this energy barrier known as activation energy. Catalysts lower this activation energy to proceed the chemical reaction. So therefore, the catalyst with high reactivity is important when designing efficient chemical process. Especially electrocatalysts are pivotal for sustainable processes such as fuel cells and CO2 reduction, CO2 capture. So this is the driving force behind the growing interest in designing optimal catalyst materials within the broader scientific community. Okay, when I refer to an adsorbate catalyst system, I'm talking about a combination of adsorbate molecule and a catalyst crystal. So the characteristic of this system can significantly vary based on the type of adsorbate molecule and the type of the catalyst crystal. So, and also the characteristic can vary how this surface is oriented and, oh, one more. Yeah, how the surface is oriented and how this molecule is observed on the surface. For example, the surface atom can be arranged either in this way and that way. And similarly, the molecule can observe onto numerous different absorption sites with a variety of orientation. So this incurs a huge, massive search space when it comes to adsorbate and catalyst system. So if you want to screen certain catalyst material, or if you want to design the optimal catalyst, then we need to go through massive amount of adsorbate catalyst combination and systems, even though we try to limit the type of adsorbate and catalyst. So like this immense variability in the chemical surface space for a catalyst presents a significant challenge in catalyst design. And density functional theory is widely used to predict the properties of atomic systems, including our observed catalyst systems. It can effectively solve Schrödinger equation, but as it's still computationally very demanding, it's infeasible to directly apply this DFT calculation to the high throughput catalyst screening for the massive surface space. So machine learning approach has risen as a promising solution to accelerate the simulation. If we have a big data set, then if we have a big data set, then we can train our deep learning model with this data set to replicate the DFT calculation. Once the training is done, we can calculate the property within seconds. So we can apply this machine learning approach to the high throughput catalyst screening. As the ML approach is a surrogate of DFT, the framework of both methods is pretty much the same. We feed atomistic structure as an input, then the model would spit out the properties of interest, like energy or per atom forces. In this study, our focus is the absorption energies, which serve as an exemplary property. And that is a key descriptor in catalyst, actually, because like that absorption energy is related to the reactivity of the catalyst. All right. So like nowadays, like machine learning approach has risen as a promising solution to accelerate replicate DFT calculation. And to deal with the atomic system computationally, we need to represent it properly. In this slide, I will explain with a simple small molecule, chloroform. Yeah, this is not actually like nothing to do with the catalyst, but like I just like take it as an example. So the simplest approach would be a string-based approach. In SMILE string, chloroform is represented as CCl3. H atom is omitted here. So like it is good for simple molecule like chloroform, but for complicated atomic system, it is very challenging to make systematic string representation like SMILE. So for the observed catalyst system, there is no well-established string-based representation. Also, we can interpret this atomic system as a 3D entity. Each atom can be represented with XYZ coordinate and its atomic number. But the problem is that the position of the atomic systems are not technically fixed. And we also need to deal with invariance and equivariance in terms of rotation and translation. So to tackle this problem, graph has been risen as a prevailing representation for atomic systems since it focuses on the interaction between atoms. Herein, atoms are viewed as nodes and the bond between them are considered as atoms. As this focuses more on the interaction between atoms or nodes, it is very effective in capturing characteristics of atomic systems. Alternatively, we can use natural language to describe this kind of atomic system. This provides a straightforward explanation of the system structure, and we also can integrate additional features as needed. So the advantage of this approach is lies in its human interpretable nature, and it allows us to include specific target features easily. Okay, as I said, graph representation is a prevailing representation, but it still requires complete understanding of 3D coordinates. For the observed catalyst system, we have two entities, catalyst crystal, and the observed molecule on top of it. So to construct the graph, we draw a directed edge between two atoms if they fall within the cutoff radius that we designate. In this sense, graph representation requires accurate 3D coordinates. However, it is not always easy to obtain 3D coordinates. Also, the graph the graph or coordinate are not easy to interpret at one glance. In contrast to graph, text offers a straightforward way to integrate observable features. Moreover, from a modeling perspective, we typically have metadata about the atomic systems. So it is unnecessary to overlook those metadata when constructing input data, regardless of the structure itself. So the text employed in the study encompass two distinct types. One is a string format, in which essential features are compactly condensed, minimizing noise from semantically irrelevant words. For example, we can create a string by combining the chemical symbols of adsorbate and catalyst and surface orientation, and the interacting atoms can be grabbed to represent the adsorption configuration. Like here, primary interacting atom represent the interacting atoms in the adsorbate and the surface, and the secondary interacting atoms are neighboring atoms of these primary interacting atoms in the surface. So like this, we anticipate this method can provide rich information regarding the adsorption configuration by grabbing this part. And this is basically about the composition of this system.
What's the definition of bridge?
That is the adsorption side. So like here, like this, like N atoms are adsorbed onto this side. And like that, there are two neighboring atoms for this atom. So like we call that adsorption side bridge adsorption site. So there are several types of adsorption sites, like hollow, bridge, and on top. Yeah.
Okay, thanks.
Yeah. While this approach streamlines the focus on the desired features, it poses challenges for manual feature inclusion. So alternatively, we can leverage generative language models to produce descriptions. For example, we can inquire with ChatGPT regarding the properties and structures of adsorbate molecule. For instance, we can ask molecule structure, like molecule characteristics to ChatGPT. Then, like it will spit out some answers regarding that characteristics or structures. And also, like we can ask whatever other properties. Of course, like we cannot guarantee the perfect accuracy, but like this is the one way to automate the feature incorporation process. So yeah, I did a small experiment regarding the reliability of ChatGPT. So like when it comes to big complicated molecule, the reliability becomes low. But still, like we can use this kind of large language model to produce descriptions automatically. Yeah. Alrighty. So yeah, let's talk about the data set now. So the Open Catalyst project is a research project aimed at addressing the challenge of catalyst screening for sustainable electrocatalyst process. This project is a joint effort between Meta AI and Carnegie Mellon University, and it provides the Open Catalyst dataset 2020. And this is the most diverse and the largest collection of the heterogeneous catalyst dataset. It comprises like over 1 million density functional theory relaxations. That means like there are more than 200 million DFT structures like this adsorbate catalyst system. So we generate the texture input data by using this structural data in the Open Catalyst 2020 dataset. The research framework can be outlined as follows. So the initial step involves converting the structured data from the OC20 dataset into texture format. Given that our input data is in a texture format, we employ a transformer-based large language model as the backbone of our work. We specifically utilize the pre-trained RoBERTa here. So we subsequently fine-tune this pre-trained RoBERTa model using both the texture data and the associated energy labels from the OC20 dataset. the texture input undergoes a tokenization process, and it is then processed through the transformer encoder. Then we extract the embedding of the first token and pass it through a regression head, ultimately yielding a scalar value representing the energy, relaxed energy. So this is the framework. Okay, given the management of a large and diverse data set, our initial focus is directed toward the specific subset in the full data set, which shows exceptional predictive accuracy with graph neural networks. Within this subset, observed catalyst system featuring this particular observed exhibit high accuracy when GNNs are used. Like this does not mean just this molecule. So like for this set, like this like blue dots represent the observed catalyst system, which contains CH4 observed. So like their catalyst materials can vary. Like this, like and CGCNN, like SNAT, and Diamnet++ are GNNs, graph neural networks. So in this case, like we can obtain the positive outcomes from CatBERTa as well, which are actually slightly better than GNNs. So the positive outcomes obtained with GNN suggest that the graph representation here effectively captures the structure-energy relationship. And considering that our texture data also highlight the structural aspect, this finding suggests that the texture representation of structure is comparably effective. Okay, for the feature exploration with so we verified the good result from the CatBERTa model with this subset, and the main advantage of using CatBERTa model is to allow it enables easier feature exploration. So for the feature exploration with CatBERTa, we employed 5 distinct types of strings, each encompassing a different set of features. Like, for example, string number 1 solely includes the type of observed, and the type of smiles means like just the chemical symbols of observed, and bird composition, catalyst composition, and its surface orientation. This is actually not enough to describe the observed catalyst system, but even with using this simple information, we can basically capture the basic correlation. And of course, the MA, mean absolute error value, is about 0.85 EV, which is not good enough to be practically used. But it's noteworthy that this CatBERTa model can process this data and it can capture the basic correlation. So what matters is how to elaborate this observation configuration by using other features. So the inclusion of the primary interacting atoms and the observation site type significantly boosts the accuracy. So the MAE for the subset falls to 0.37 EV, which was as seen in this parity plot. And for the overall MAE, it also drops significantly. And also, like if we add secondary interacting atoms to the string, then we can even further lower the MA value across the entire data set. So like this, primary interacting atoms and secondary interacting atoms help CatBERTa model captures the structure-energy relationship. However, in string type 3, we enrich our feature set by incorporating the additional atomic properties like dipolarizability, electronegativity, and electron affinity, and so on. However, this effort does not affect the overall MAE. This shows the same overall MAE with the string type number 2. That means like these atomic properties are already embedded in the atomic symbols illustrated in the observed smiles or bird composition. So like these are pretty much unnecessary information. We can verify this in a data-driven manner. And also for the string type 5, like we added bond distance of the primary interacting atoms. But this also does not help boost the accuracy when it comes to the total MA. So the bone distance is also not a generalizable feature, which can help the model capture the structure energy correlation. So as such, we can effectively explore the feature space by conducting an evaluation study using different text input data. Okay, in a previous slide, I showed the result from the string-based input data, but like we also use description generated by ChatGPT or RoboCrystallograph. So we generated textual description by using two distinct methods for this case as well. So the first type contains general information about the observed molecule and the structure of the catalyst crystal. In contrast, the second description is designed to include features related to the absorption energy modeling study, such as coordination number and the electronegativity. Like this is an example. So for the description number one, we just asked ChatGPT about the general information, like what is the structure of this molecule, observed molecule, and it would give us the answer like this is a triatomic molecule consisting of something, 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 which is actually not perfectly correct because actually NH3 is not a triatomic molecule, but it can capture other properties pretty well. Like the bond angle is about 107.5 degrees and its bond length of 1.01 Armstrong, something like this. So we can gain the basic information about this molecule, and we also can obtain the basic information about this catalyst material by using RoboCrystallographer. It can generate description regarding the structure. And for the description type 2, we specifically ask some properties which is used in the absorption energy modeling study. So this is grounded on the previous scientific research. So we asked ChatGPT about what is the coordination number of this molecule and what is the electronegativity of the atoms in this molecule and the catalyst material. And then the ChatGPT generate description about our question. So we have two distinct types of description. And the result is we can obtain better result from this description type 2. So yeah, this approach allows us to assess the attributes employed in the modeling study through a data-driven perspective. So here in like general information, the features based on the scientific research definitely helps the model to captures more relation between structure and energy or like feature energy relation compared to the general information in the description type number 1. Alright, so now let's proceed to compare this result with other GNNs. In the table below, you will find various columns representing different aspects. So we compare our CatBERTa with GNN such as CGCNN, Jeanette, and Diamond. And data slides represent the size of the training dataset. And the subset refers a specific subset that exhibit high accuracy for both GNNs and CatBERTa, which is seen in the parity plot slide. And total represents the entire validation dataset. And in domain means the systems in the validation set where both the observed and catalyst are seen during the training. While the out of domain represent systems where there is a specific entity which is not seen during the training. For example, out of domain observed, like this, like systems in this domain contains observed which are not seen during the training. So yeah, let's focus on 10K case first. In this case, CatBERTa demonstrates enhanced effectiveness compared to other GNNs. So this obviously shows better results, lower MAE compared to other GNNs. But however, when the data size is increased to the 100K, the total accuracy slightly lags behind other GNNs. But still, for the subset, it shows comparable or like slightly better result compared to other GNNs. So this means, like, of course, like this will be our further challenge. But still, for the systems where the energy and structure relationship is pretty much evident, our CatBERTa model can capture that relationship pretty well. And for the smaller data set, like obviously CatBERTa shows better performance for those limited data size. So if we have limited size of data, then we can maybe consider using textual representation to train our model and predict some properties. And like this, lagging behind accuracy is mainly because of the unseen observed molecule. The poor accuracy observed in out-of-domain observed and out-of-domain both cases compared to other GNN. Like these are the reasons. So this will be, addressing this challenge is among our future research plans. Alrighty. And another like good advantage of utilizing transformer-based large language model is its interpretability. By analyzing the attention score, we can discern which tokens receive more emphasis within this model. Here, I display the attention score for individual tokens in the first hidden layer and the last hidden layer. The uppermost row is about the string type number 4, and this is about description 1, and this is about description 2. These are just exemplary cases. So the brighter, so how do I say this? So the brighter color represents the lower attention score, and a redder color represents it gets more attention score inside the model. So yeah, in the attention score of the first hidden layer, we can clearly observe strong relationship between adjacent tokens. Like we can find more colored tokens in this first hidden layer cases for all like string type or description type. But once the tokens are passed through the hidden layers and it gets to the last hidden layer, then the attentions are condensed to the specific vocabularies. So as these tokens pass through a sequence of hidden layers, they become increasingly focused on specific sections of the text. This transition results in a fewer vocabulary element receiving high attention in the final hidden layer compared to what is observed in the initial hidden layer. One intriguing observation in the string type is that even though we did not explicitly provide information about which atoms belong to observed or catalyst entities, the model is inherently placed greater emphasis on interaction between surface atom and the observed atom. So like here, these chromium atoms belong to the catalyst. Actually the surface of this catalyst, and this nitrogen belongs to the observed molecule. We didn't tell anything about like which atom belonged to which, but like it placed higher attention toward the surface atom and the observed molecule. So yeah, like through this analysis, we can gain an initial understanding of the interpretability with regard to the model's emphasis on specific features. Also, embedding analysis can provide another valuable insight for the interpretability. So the first row is the embedding Disney plot before fine-tuning, and the lower row is the embedding Disney plot after applying fine-tuning. So before undergoing fine-tuning, the embedding reveals a limitation in effectively captures the type and size of the observed. embedding associated with the identical types and sizes observed do not exhibit clear clustering here. Everything is intermixed. But once it goes through the fine-tuning process, the model excels in distinguishing between the observed type and observed size. We can see the clear clustering after the fine-tuning case. As for the catalyst type, before applying fine-tuning, yeah, it is better at capturing specific catalyst types. So the embeddings are not intermixed. So it obviously captures like certain catalyst material which contains the same atoms. So like here are catalysts which contains zirconium atoms. Okay, so model is able to differentiate this catalyst material. But after the fine tuning, actually the embedding testing plots are pretty much intermixed. So that means the fine tuning process make the model focus more on the observed section instead of the catalyst section. So the fine-tuning process carried out without explicit specification of observed type, size, can refine the model's focus, directing it more precisely toward the observed section. So like embedding analysis can add another interpretability to the transformer-based large language model. Okay. Yeah, now let's conclude. Yeah, there are numerous intricate details related to the catalyst, observed, and energy prediction. However, what truly matters is that the atomic systems can be represented by using text or natural language, and we can leverage large language models to process the data. And the primary advantage of employing text representation is the flexibility in incorporating target features, especially when compared to complex graph representation that require precise atomic coordinates. And additionally, using transformer-based large language model can provide interpretability, as we saw in the attention score analysis and embedding analysis. So yeah, our paper represented initial exploration in the field of catalyst materials. However, this approach can evidently be applied to various other atomic systems. Our research group has already published several papers this year in different domains, like peptide BERT. This deal with the peptide, and that informer deal with crystals and metal-organic framework. And we recently released GPT-MoBERTA, and this is about small molecule. And for this case, actually, we could achieve SOTA result compared to other GNN models. Okay, thank you for listening to my presentation, and I'm happy to address any question you may have.
Thank you. Thank you for your talk.
Hey, first of all, thank you for your talk. This is Adar from Brown. I had a couple of questions actually. I'll start with one. So can you like maybe pinpoint where you're actually using ChatGPT and when you're using BERT? Because most of the analysis I see is based on embeddings, right? And embeddings, I assume you got from BERT.
Oh yeah. So the embeddings are okay.
Like, what's the synergy between ChatGPT where you cannot actually get the embedding and the BERT?
Yeah. So first, like the embeddings are from the transformer encoder. So like I just like grab this embedding from the transformer encoder, and then I plot that testing plot in the last slide. That's one thing. And for the ChatGPT, we use this tool to generate the input data. So in the Open Catalyst data, we only have in the Open Catalyst data set, the whole atomic systems are represented as a 3D coordinate. So we have trajectory of this system. And so we convert that trajectory, like 3D coordinate, to the texture representation. So one way is to convert that information to the texture screen. For this case, I used PanaGen software to grab this information. But to do this, we need to manually select the feature and write a function to generate this thing. So we were thinking of how to automate this process. So why don't we just ask some kind of features to the ChatGPT or some other large language model, generative large language model? So, okay, our system is NO plus titanium and palladium crystal catalyst. So we can just ask what's the property of this nanomolecule and what's the structure of this catalyst to generative large language model. And that would generate description for that thing. So in this case, like we don't need to use any 3D coordinate from the Open Catalyst dataset. We simply use the metadata for the system and then ask that to the ChatGPT or RoboCrystallographer to obtain the input data.
Got it. So if I understand correctly, you have two steps. One of them is like going over the data set and using ChatGPT to extract the features that you want. And then you're creating those descriptions, which are a new data set, let's say. You pause there and go to the second step where you take those descriptions and learn using BERT their classification. That what you want to.
Oh yeah, almost correct. So for that, yeah, embedding class. Actually, like I didn't implement any classification task here. Like this is generated from
I meant classification of like exactly what we see right now. Like those clusters are some sort of classification. Like you're trying to figure out. I understand. Okay. Thank you. And if you don't mind, like one more question about the. Can you go back to the clustering, like?
Yeah, sure.
Embeddings clustering. So I assume you're doing some PCA or TSNE, right?
Oh, here
you have to. What?
TSNE.
TSNE,
yeah.
So my question was I forget. So when you do TSNE, you're kind of creating. I wanted to ask if you're doing the TSNE before or after, like you have a fine-tuned model and a non-fine-tuned model. So you just take the embeddings that came straight out of your model, and then you put them into a TSNE as a batch, like on all of your sentences at once, or you do it in a previous step or something like that.
Oh yeah. So okay, to answer your question, I use pre-trained RoBERTa. So like this RoBERTa encoder is already pre-trained with the English corpus.
Yeah.
So this
you're
like before
you're producing all of the embeddings using RoBERTa, right?
Yeah, correct.
And then when you have a matrix of like number of samples versus the embedding size, you do the TSNE on that, right?
Sorry. What's the last part again?
You go through the RoBERTa before fine-tuning, let's say. You have a matrix of size, number of samples versus size of embedding. And on that you do TSNE, right?
Yeah.
So, and then there's the clustering process, right? Does it happen before the TSNE or after the TSNE?
Clustering before or after TSNE? I'm not so sure whether I understand your question correctly, but
when you do clustering, right, you can do high-dimensional clustering and you can do 2D clustering.
Oh yeah, I just like directly go to the 2D clustering.
Yeah, so that's an issue because TSNE loses information. You're reducing dimension.
Yeah, correct.
I would do I would suggest doing the clustering on the embedding, like high dimensional clustering, and then keep the labels, and then do TSNE and put the labels.
Okay. Yeah. Got it. Like I tried a bunch of different dimensions for the clustering, but yeah, I got the point. Yeah, maybe I should like apply the analysis
Yeah, because
for
because
the
both
embedding.
TSNE, PCA, whatever you use to reduce
Yeah.
dimensions,
Mhm.
when you reduce to 2 dimensions, you lose information for sure.
I know.
Yeah. So you want to do the
Yeah.
clustering before you lose information. That's what I'm saying.
I know. Yeah, but
Yeah.
the purpose of like this analysis is whether there is any type of like clustering. I mean, any type of change before and after the fine tuning process. And then obviously, yeah, the fine tuning with the energy label can redirect the model's focus more on the observed section. And that is also can be captured by the section-wise attention score as well. So like before the fine tuning, models focus more on the Berg section, catalyst section, but after the fine tuning, like its attention direct toward more on the observed section, even though the lengths of the tokens are much smaller. So anyway, but I got the point.
No, I
Yeah.
agree. I agree. I think like this analysis is important, and I agree that you want to show the before and after fine tuning. I'm just saying like you are losing information that might change results of the clustering. So to comparison, like your comparison is valid and important. Just to make it fair, you need to do the clustering before. That's yeah.
Thanks for the advice. Yeah.
Have you seen a paper on Graph GPT?
Yes.
So wouldn't that do everything that you need actually?
One moment.
Graph GPT. Let me just put it on the. I'll put it on the chat.
Okay.
It came out recently, from Hong Kong, but I think it does pretty much everything you need. It has the text, it has the graph structure, it has. They haven't applied to Catalyst yet, but it seems to me that it has all the features that you need.
Okay. Let me look over it. So, but like it still use. Actually, this is very similar to what I am doing right now. So my next plan is to use like graph representation and text representation simultaneously to improve the prediction accuracy. So actually, I'm doing this. Okay.
Yeah, it is very similar. It's just general. They don't just do it for Catalyst or can be used for anything. Actually, it could be used for climate. It could be used for any applications that causal inferences could be used for just through text.
Yeah, actually, I already got the result from this multi-view training. So once I apply that like GNN embedding to the text representation training, I could improve the prediction accuracy. So yeah, thanks for the advice. Yeah, I may need to take a look at this paper closely.
Yeah, they have the code and they have everything. It's a group from Baidu and Hong Kong, and
I feel this moving forward quickly.
Yeah.
Thanks.
Great talk, by the way.
Thank you so much.
Are there any other questions from the audience? All right. Thank you for the presentation. We're going to move to our second talk. You're welcome to stay here. Our second speaker is Yan from PNL, who is currently a senior data scientist and the principal investigator in the physics and computational science division at the PNL. Yan has a PhD in control engineering from Slovak University of Technology in Bratislava, Slovakia. And before joining PNL, he was a postdoc at the mechanical engineering department at Katholieke University Leuven in Belgium. his current research is focused on differentiable programming for scientific machine learning, constraint optimization, and model-based optimal control with applications in the energy sector. And I would like to apologize. The title for this talk is actually wrong. It's not about language model. It's about neural Manser differentiable programming language for data-driven modeling and control. So, can you hear me? You're muted. You can start the presentation.
Yeah. Thank you, Janghoon, for the introduction, and thank you very much, George, for the invitation. It's really an honor to be presenting in front of this group, one of the founding groups of scientific machine learning. Can you see my screen?
Yes.
Great. So we are pretty much following in the footsteps of giants. The role of National Lab is to take promising ideas from academia and deploy them and scale them in applied context. And that was also the story how we started developing our library, because at the lab we are interested in heterogeneous simulations from multitude of domains, because they are crucial for many areas of scientific discovery and decision making, but we are suffering from computational demands of these high fidelity simulations, whether we are talking from density functional theory, from molecular dynamics, like we heard from the previous talk, or when we are talking about energy systems in the engineering scale, from buildings to power systems. There is a need not only to accelerate the simulations in the forward sense, but also to enable them to be embedded in real-time decision-making, closed-loop control schemes. So how do we embed these simulations in optimization is still like an open challenge. So luckily, many teams have been working relentlessly on scientific machine learning and physics information learning in the last couple of years, and we see more and more headlines how these methods are very promising to bring scalability and control-oriented methods in the field. So when we look historically on these methods, we have model-based domains, be either constraint optimization or differential equations, which are fully physics-based. We know everything and we use numerical solvers to obtain solutions. So this could be some interior point methods or active set methods for constraint optimization, or it could be some finite element methods for differential equations. On the other hand, computer science community was developing mostly data-driven methods, supervised learning, reinforcement learning, where you are doing inference based on statistical models from samples. And these two domains has been historically divided, not only in theories, but also in tools they have been developing and using. So we have wonderful packages for constraint optimization. These are algebraic modeling languages that allow you to formulate your problem in high-level abstract form, and then they parse the problem into solver-specific language, and pretty much similar for all sorts of differential equation, either general purpose or tailored for specific scientific domains, whether power systems or molecular dynamics. But really the revolution in modern computational science came with deep learning, like roughly 10 years ago, where libraries like PyTorch, TensorFlow democratized deep learning to masses. It's so easy to train neural network models these days that every single researcher is doing it. So that's why they are so popular, because they're extremely easy to use, they're high performing, and they have very good community behind them. So new features are being rolled out every day, and you have excellent hardware accelerator support with modern compiler technology. So that's what we see is the future. And it's not only deep learning, it's general scientific machine learning or differentiable programming, which is really unifying approach that allows you to compute sensitivities of complex computer programs, not only layers of deep neural networks. So everyone knows backpropagation is used for training deep neural networks, which is reverse mode automatic differentiation algorithm. But there are all sorts of automatic differentiation algorithms forward mode, reverse mode, adjoint type methods that fall under the umbrella of differentiable programming. And this allows you to compute the gradients for gradient-based optimization for very complex scientific models. We started to work in this area 5 years ago, where the field was only emerging. And here are a couple of papers that influenced myself, and they are biased and incomplete literature review, but I would like to highlight a couple of those. A differential programming paper from scientific machine learning community in Julia. Of course, spins from your group that revolutionized the way how we can solve PDEs. Neural differential equations that allow you to not only learn surrogates for dynamical systems, but they're essentially the engine that is running generative modeling these days, stochastic differential equations. That's basically what is behind score-based matching methods. Differentiable optimization methods that are getting traction in operation research community for learning to optimize and predict to optimize for large logistic networks or power system optimization, like AC optimal power flow or recommended dispatch problems that have a large scale impact. And once you have all of these components, that you have dynamical system model surrogates, you have means for systematically handling constraints. When you put them together, you have differentiable control. So I'm very excited about where the field is going, both from the theoretical perspective, but also from the perspective of the algorithmic and software development. But these 5 years ago, when we started to work in this area, there was not that many open source libraries that would be like high performant or easy to use. So we started developing our own library just to increase the productivity in our projects. And it was most developed as a proprietary tool at PNL projects, but we quickly realized that user-friendly library can not only be productivity tool internally at PNL, it can be something useful for the whole community. So we decided to open source this scientific machine learning library that we call Neuromancer, which is essentially productivity tool for all sorts of scientific machine learning problems, allowing you to formulate your problems in high-level abstraction language, which would be your mathematical equations. We have very user-friendly command line APIs for writing those equations and systematically combining them with modern deep learning architectures in what is called differentiable optimization problem. And what our library is doing behind the hood, it's generating computational graph, or quote unquote physics-informed neural network architecture with PyTorch as a backend. So when you are familiar with algebraic modeling languages for constraint optimization, they are doing something similar, but they are parsing the constraint optimization problems into specific form of a solver, whether it would be commercial solvers like Cplex or Gurobi, or open source like interior point IPOP method. Here we are doing it for machine learning. So here's just a mock-up sequence of steps. You have some abstract problem, nonlinear objective, nonlinear constraints, and you want to train neural network that solves this problem. So you would like to define those problems in a symbolic way, because that's how most of the science and engineering domains think first. These variables represent some physical quantities like speed, acceleration, pressure, temperatures, and you are building the problem on top of them without thinking about dimensionality and data types yet. So this fully symbolic layer is the interface that allows you to formulate these scientific machine learning problems without a lot of hassling with data science, wrangling of data and transformations. In terms of capabilities, We support several domains. First domain is learning to optimize. That allows you to solve constraint optimization problems. You can do it either by imitation learning, where you have pre-computed solutions from your iterative solvers, and then you just want to minimize these residuals, or you can do it in so-called differentiable way, or self-supervised constraint deep learning, where you are computing sensitivities of the optimization problem objectives and constraints to provide the gradients for the neural network training. And I will quickly show you that really conceptually it's the same than training physics-informed neural networks, PINs. So here are just few examples. Like on these GIFs, what you're saying, each frame is a new instance of your optimization problem. Your feasibility domain can change, your objective function can change shape, and you want to find the optimal solution of this. When you would do it with classical methods, you would need to recompute the problem every single time you change the parameter. Every time I'm changing the constraints here, the new frame is iterative solver running again. This can be very computationally demanding, especially for real-time decision-making. The power of scientific machine learning that you can do this offline. You pre-compute the solution on the distribution of these problems, and now we have neural network that represents the surrogate of an optimization problem. So I mentioned physics-informed neural networks. That's essentially the idea behind learning to optimize. But we are also working on modeling abstractions that are familiar from engineering domains, like people from MATLAB Simulink control engineering background or mechanical engineering background, developing models in languages like Modelica. They think in component-based models, causal or acausal, but still, like, you have component that represents some subsystem of the larger system you want to model. And what is lacking in current tools from engineering domains is the heterogeneity, that we could replace physics-based components with black box components and gray box components, and then use them in gradient-based optimization. And these priors can include constraints on stability through some linear algebra factorizations or assumptions on the network dynamics of the system, and doing really like continuous time graph neural network modeling. So that's what we are currently supporting in the library. And once we have these surrogate models, we can do control, closed loop control, which is conceptually, again, very straightforward extension. You have your surrogate model or white box model differential equation, PDE, and you combine it with a control policy. That will be the generator of your control actions that will be the perturbing the model, and you will do the rollout over predefined prediction horizon, obtain the trajectories of the system, and now you evaluate the residuals from the control objectives and constraint penalties. Very similar what you would do in PINs, but now instead of just neural network giving you solution of the PIN, neural network gives you so-called like hidden states of this dynamical system, this closed loop dynamic system that you can differentiate through and optimize over distribution of your domain, which typically would be control parameters like initial conditions, boundary conditions, and some performance scaling factors like price signals for economic optimal control. And it turns out that you can solve a lot of control problems in this way. You can stabilize unstable, linear, nonlinear dynamical systems. You can do trajectory optimization, obstacle avoidance. You can even combine new fancy methods from computer science that allow you to learn some feasibility, stability, and constraint satisfaction certificates for closed-loop dynamical systems, like example of neural Lyapunov functions or control barrier functions. So very nice.
Yeah, can I ask a specific question? Because since you mentioned obstacle avoidance, so with Jerome Darbon that you saw earlier, and Janghoon, one of the PhD students in the group, and others were trying to do drones and avoid collision, go fast from one side to the other, and so on. And comes Jacobi-Bellman equations and pins and some fancy stuff. But so how can you just take, let's say, two drones or some a specific example and guide us, take us through these steps so we can see actually how we can implement this, because it sounds very powerful, but I hear it, I hear you and I see it at a very high level, but I cannot grasp exactly how I would do it.
Yeah, that's excellent segue, because right now I want to go to the library and show some Jupyter notebooks.
Okay.
Yeah. I want to give high-level overview how all of these methods are actually still fall in the same category of methods, one coherent framework. That's what I really love about it. So I'm going to show some of our tutorials on the GitHub/pnl/Neuromancer. And we have extensive README, and I will, so I can do like maybe 1 or 2 examples. I don't know how much time do I have left. Maybe 20 minutes, 15 minutes.
No, you have time.
Okay, so I can either hop directly in the control example, or I can first show pin example.
Yeah, just go you can start with a pin example. Just do it your way.
Good. So I will start with pin example because I think that's the foundation. And of course, we are replicating the results from your paper from 2017. I don't think I need to introduce pins. I'm just going to walk you through the API of this library. Everything is written using PyTorch as a backend, and then using Neuromancer as high-level symbolic abstractions. So here, let's have this simple diffusion equation, some initial and boundary condition, and we want to train this using pin method. So what do we need to do? We sample the initial conditions, boundary conditions, and collocation points. So I'm going to skip these cells that basically do the sampling, but you can visualize this is small 2-dimensional domain. Blue dots, you have collocation points where you want to enforce your PD constraint, minimize the residuals from there. And you have red points on the boundaries that will provide you with supervisory signal on initial and boundary condition. So I want to have a neural network that will map this domain, spatial and temporal coordinates, in the solution of PD. So I'm going to instantiate PyTorch neural network. Here I'm using some predefined multi-layer perceptron from our library, but it can be really anything. It can be any Torch NN module. It can be residual neural network, recurrent neural network, LSTM, yeah, you name it, graph neural network. And then what I'm going to do, I'm going to wrap it in the class that we call node. This is the class from our library that is doing symbolic wrapper, because everything you do in deep learning framework is a computational graph that is making transformations on tensors that are primary data types. In our case, we will be working with dictionaries where we have string values for variable names, and each variable string name will have associated tensor value. And this way, this allows us to construct these symbolic computational graphs. So for the PDE solution, we want to map state and time coordinates into the solution of the PDE. Let's call it y hat. So that would be my solution network. But I want to enforce physics-informed neural network layer. For that, my pin needs to satisfy this equation. And we see that that requires some automatic differentiation of our neural network with respect to time and space coordinates, and also requires some mathematical expression like trigonometric function. You could write this as a layer in PyTorch, write your own custom NN module to represent this pin. But what we are doing here we provide the user with ability not to do that. That's just to write the minimum abstractions on a high level, symbolic level. And for that, we will leverage the variable class from our library that allows you to instantiate symbolic handles for the variable like y hat, t, and x. And you know that this y hat is coming from the neural network output over here. And x and t, these are variables that are domains, so we are sampling them from the data set. So, okay, now I have these three variables. I can leverage our operator overload approach to construct new derivative variables out of these just by calling the grad method on variable. And this will give you the derivative of this PD solution with respect to time, first derivative with respect to space, and second derivative with respect to space. And now you have new variables that you can use in your pin layer, in your PDE. And it's really just writing the expression on these symbolics that is interoperable with arbitrary PyTorch callables. So when you have torch exponential, torch trigonometric functions or constants, you can write them in one line of code, as opposed to writing the whole new class. And what you get is new variable that now allows you to represent this physics-informed neural network layer. Okay. When you show the computational graph, it can be very messy because there are many components, but now you basically have custom physics-informed neural network architecture without writing many lines of code. You have written like 4 or 5 lines, and you want to train it. So what kind of physics-informed loss functions you can introduce? Well, you want to minimize the residuals of your pin to satisfy the PD constraint. So you want to drive this value to 0 over the samples of the collocation points. And then you want to minimize the residuals from the supervisory signal on boundary and initial conditions. So you will have some known values of your PD. So you minimize this. And you can even bound the solution domain to be in the bounding box or more complex constraint. And you put all of these terms together. Again, in the code, it will be few lines of code. You can design what type of scaling factor you introduce in individual pin loss terms. So the first one, over the collocation points, the PDE residual, you want to drive it to 0. The boundary and initial conditions, you have some supervisory signal, and you want to minimize the residual with respect to that. This one is coming from the data. This one is coming from a neural network. And you want to minimize the violation of some kind of bounding box constraints on the domain of the solution of the PDE, because we know that this particular PDE will be in the domain -1, 1. So now we have 4 terms that will constitute your physics-informed loss function. And you can put them all together in various ways. The most straightforward approach is just to sum the penalties of these violations. So that would be the penalty loss, what I'm having here, that hands over a list of objectives, list of constraints, and gives you this pin loss that will give you the scalar value on which you can compute the gradients using backprop method. We do have implementation of more fancier methods, whether it is like barrier penalty methods or augmented Lagrangians, but just for the sake of introducing the API for the library, I will stick with the penalty method because that's the most intuitive one. And once you have the pin loss function, you want to use it to train your neural network architecture, the PDE net that will solve the pin. And it can come in a list of nodes. So right now I have one neural network, but in more complex examples, I can show you how can you solve ensemble of neural networks, or how can you train complex cyclic or acyclic computational graph composed of trainable components. So that will be leveraging the control example when you have a control policy and some dynamic system surrogate. So what I am having here is differentiable constraint optimization problem that is going to train the PDE network, which is multi-layer perceptron in this case, to minimize the physics-informed loss function to solve this diffusion equation. And everything is working with PyTorch as a backend. Therefore, we are working with standard PyTorch optimizers, in this case, ADAM stochastic gradient descent, that will be handed to the trainer class using data loaders. We are using standard PyTorch data loaders with dictionary as our primary data type for sampling your forward pass. And everything else is very familiar hyperparameter setup, like number of epochs, whether you want to print epoch or whether you want to have some kind of early stopping mechanism. You can have learning array scheduler, all standard deep learning infrastructure is supported. And then you just have a trainer that has your model, that has your data set and all the hyperparameters, and you call the train method, wait for convergence, and you obtain the best train parameters, which you can now visualize. What I'm taking here, the problem has this neural network, so I'm taking it out and I'm doing forward pass on this neural network, given the test data dictionary, and I'm obtaining the solution, which will be also dictionary. That's why I'm taking this y hat, which is representing the variable of the PDE output. This is just transformation to represent it for nice plot, and you are obtaining the solution of the PDE. So what is the motivation behind this library? Is a productivity tool for domain experts who may not be experts in scientific machine learning or numerical methods or PDEs, but they do have a high-level problem they want to implement and deploy very quickly. So that's why we are providing these higher levels of abstraction. Any questions on the API at this point?
Jan, can you highlight some of the difference from a straight implementation, let's say in DeepXD using PyTorch? What are the differences for somebody like me that...
Yeah. For instance, sorry for scrolling. I think I have a reference. Maybe this one, or this one, for a comparison. Let's say pin diffusion equation. Yeah, so this is exactly the same problem I was showing with this symbolic API. So let me scroll down. This would be your neural network in straight implementation in PyTorch from ground up. So you see there is a lot of utilities that are error prone and can be clumsy for someone who is not familiar with deep learning and scientific machine learning. So this can be like gibberish for domain experts, because you need to really be careful writing your forward pass in the right way, having all the attributes in right format, parameters to be locked as trainable parameters and constants as constants, and then you need to compute your loss functions and really call like the lower level callables like the autograd, and that requires a lot of input arguments that are not necessary for the user to know, and like handling with the shapes of your tensors. So this is just an example. What would be the pin implementation for this simple diffusion equation from basic PyTorch, as opposed to as opposed to this.
Yeah, I see. Yeah.
Yeah. In the end, this instantiated object is still NN module. So it behaves exactly the same way like this piece of code, but we are reducing the number of lines the domain expert need to write, probably by order of magnitude.
Hello, this is Lulu. Just a quick answer to the Joel's question. So if we compare with DPSDE, the difference is so in order to implement this equation, differential equation, so in DPSDE, from the very beginning, first line of import to the end, maybe we need 20 lines. Basically, DPSDE do everything for you, starting from the sampling, so one line for sampling. So basically, you have everything. But here, I think in this library, it focuses on the differential part. For sampling, the user has to be implemented sampling by yourself, define the geometry, define the boundary condition. So, but DPSDE for Newman boundary condition, periodic, everything is in every one line.
Oh, correct. Yeah. So what we are intending to provide is like really the focus on formulating your problem in few lines of code in symbolic computational graph, and we are aiming at different scientific machine learning use cases. So we are not like PD library, we are not OD library, we are not just learning to optimize library. That's why we are not providing the data loaders for all of those specific ones. What is the vision and the philosophy behind the library is to be interoperable with PyTorch ecosystem. So if you have your data loaders already implemented in PyTorch, you can just bring them in here and import them as a standard PyTorch data loaders, and then use this library to construct your problem.
But Lulu, can you not combine the two then?
We could combine this. Actually, one idea is we can apply this inside DPSDE.
That's what I mean. That's what I mean.
Yes.
And
exactly.
I would be very excited about this because I want to work more about the integration of different scientific machine learning libraries that are written on top of PyTorch in kind of scientific machine learning ecosystem. We're very much inspired by what they are doing in Julia with their SciML ecosystem. I see that there is a potential to do this with more deep learning, computer science centric tools.
This is a good project. Lulu is actually a DOE Young Investigator awardee.
Perfect. And I'll be more than happy to chat offline and explore potential integrations between.
He's a deep XD author also. So
perfect. Yeah. Yes. Yeah,
he's now at Yale University, so that is his contact. He just moved from UPenn.
Good. Yeah. Happy to chat. Yeah.
And also I'm thinking the UQ library by Zhongren. Essentially, we can have a much larger ecosystem by combining all these libraries, interacting with each other.
Exactly, because like you cannot have one team with limited budget and manpower to do it all.
Yeah. Jan, do you know what he's talking about? A neural UQ?
Yes.
Neural UQ is a library that has Bayesian and ensemble methods, and one of my other students, Zogren, who is hosting today, is the author of it. So that's a good idea, Lulu. Let's pursue that, because I mean, Jan is at PNNL, so we are all affiliated with PNNL, so that's great.
Yeah, that's easy pathways for collaboration. Yeah. So next example, if I have time, I want to show you very quickly running through learning to optimize.
Yeah, you have time, Jan, don't worry.
Which is very popular in operational research in power system optimization. And I'm going to show you this simple high-level conceptual problem where you want to minimize some nonlinear objective functions subject to some non-convex constraints. And this is standard two-dimensional test problem in optimization that's called the Rosenbrock problem. What I want to highlight is the same API that I just used for formulating pin problem, and the same infrastructure for solving pin problem I can use for learning to optimize methods, because the concept is exactly the same. I'm importing PyTorch and Matplotlib for visualization, and I'm importing all the necessary classes from our library. So I start with sampling the domain. Here I have two parameters for convenient visualization and sampling my data dictionaries, which will be looking something like this. A and P, one parameter for constraints, one parameter for shape of the objective function, and I'm sampling these collocation points in the parametric space to enforce the solution of this constraint optimization problem. And I have training and test set data. So I use, again, neural network to map the parameters into what is called primal solutions of the problem. Again, multi-layer perceptron, and again, I'm wrapping it in the node class to make it symbolic. So I have this optimization problem in a symbolic way. Now I want to enforce these objectives and these constraints. I'm going to instantiate two variables. I'm using splitting here because I know this will be two-dimensional tensor, number of batches and number of variables dimensions. And just for convenience, I'm creating two variables because this equation now looks nicer. That's the Rosenberg equation. When I instantiate this equation, I can call the minimize method, which will spawn my objective function term. In PDEs, like we know that PD residuals needs to be equal to 0, but very often in constraint optimization, we have just some kind of expression that we don't know what should be equal to. We don't know what is the value of the global minimum of that function. So for that, we just want to minimize this objective as is. This is the instantiation of the three constraints that will be half donut shape. And now I could just use it as it is and train it as I did before, but I'm also going to do something fancier and to add one so-called implicit layer. In this particular case, it will be differentiable gradient projection layer, where my neural network will give me solution. But this solution sometimes can violate constraints. And we want to have some kind of feasibility restoration methods to guarantee the solution will be in the feasible domain. That's very important for safety critical applications in power system, in robotics, when we are dealing with control. So that would be another layer. And it's very simple implementation. It's basically iterative algorithm where you are taking gradients of the violations of the constraints and you're taking some step towards correcting that. Okay, so how can I do that? We have implemented this method as an implicit layer in the library. You can specify a number of constraints you want to correct and what would be the variable to be corrected, and then provide all the hyperparameters of the projected gradient, what will be the step size and decay parameter. We also have example when you can use like CVX layers, which allow you to do projections on arbitrary convex sets. But this is just one method I want to highlight. So what you're ending up with now is optimization problem that has one objective term, three constraints, and you have neural network that you want to train to give you the solution. And then you have this implicit layer, which is iterative solver that will be correcting the solution of the neural network. And you are using now the same APIs to create penalty loss on objectives and constraints that will be training the list of these components in the computation graph. Let me show this computation graph. Yeah, so the computation graph on the high level would look like this. You're sampling your domain, your collocation points in a parametric space, A and P. You're providing them as inputs to your neural network mapping, giving you primal solutions. And the projection layer will be guaranteeing that you will stay in the feasibility domain. And this will be penalized with respect to list of constraints on objective that will be aggregated in pin loss function. And you are going to train this with automatic differentiation with backpropagation to tune these parameters. So you see, it's really the same methodology than you are using in pins. Pin loss functions and neural network, and in between you can have some implicit layer, some solver. Okay, the same story here, stochastic gradient descent, the same trainer, the same API for training. I'm going to skip this just to get you some visualization that I'm comparing against interior point method implemented in CatBERTa framework, that is nonlinear optimization framework. So you end up something like this. I deliberately train neural network to perform bad by providing it not enough training samples and training epochs. So my neural network would give me like first shot, oh, I want to be here. And then the implicit layer will provide you with the correction steps to get you to the feasibility region. So that's conceptually how learning to optimize is the same than physics-informed neural networks. And why I'm excited about it, because they are, again, two originally different domains. Applied math for PDEs and collocation type methods versus operation research and sensitivity analysis of constraint optimization problems that have different theories, different numerical tools. But now the scientific machine learning allows you to build bridge and take inspiration from theories from one domain and incorporate it in another domain to obtain some kind of improvements on existing methods. Any question on learning to optimize or general API here? If not, I'm going to show you the last example, which will be learning to control. Skipping the installation part. Here I am going to learn control policy parameterized by neural network to govern the levels of liquid in two interconnected tanks by modulating the mass flow and two-way valve of the system. So this is hello world example in nonlinear model-based optimal control. If you would approach this with reinforcement learning, you would need to have the model of the system wrapped in some kind of environment like OpenAI Gym and sample the hell out of it to learn neural network control policy. Here we are going to do something in between of deep learning and model predictive control. We assume that we know the systems of the ODEs. If we don't know, we can do system identification or neural ODE or universal differential equation or do parameter estimation of existing ODE. So this will be nice nonlinear ODE that I assume I know. So I'm just instantiating over here. And it will represent my system model in the high level conceptual computation graph. And I want to train the control policy here. And I will again sample collocation points in my control parametric space. And I will train this on physics-informed loss function, minimizing control objective like reference tracking and constraint satisfaction. So the control policy will be mapping states and desired references into control actions that will be perturbing the system, and the system will be solved by ODE solver. Oops. So overall problem formulation looks like this. This is standard parametric optimal control problem, where you want to minimize the residuals between your states and desired references. This is the reference tracking objective. Typically in model predictive control, we are using some kind of terminal penalties for stability, that at the end of the rollout, your state is very close to some terminal region. And we are doing this over prediction horizon and steps. The difference between classical online model priority control is that you would need to recompute this problem every time you're changing initial conditions, your references, or constraint parameters. Now we are going to solve this offline by training the parameters of this neural network. This is the control policy that will be mapping our control parameters, initial conditions, and references into control actions, and we will do the rollout on the ODE. For this ODE, you can use any differentiable implementation of the ODE solver in PyTorch. It could be through adjoint method, or it could be just unrolling the operations of your ODE solver like Euler or Drgona. So how do you do that? Here, I'm sampling the control parameters that would be my initial conditions and desired references in a dictionary dataset, and using standard PyTorch data loaders, the same APIs that I used for learning to optimize and for PIN. Okay, now I'm going to take the ODE. This is the ODE I implemented before with known equations, and I'm going to integrate it with the Drgona integrator in this case with some predefined time step. So this will be still tensor to tensor mapping because it's implemented in PyTorch. It's PyTorch NN module. So it's discretized ODE system over given sampling rate. I am going to make it symbolic again with using the node class. And I know this is non-autonomous dynamical system. Therefore, I require some states and control inputs. And I will obtain next state at the next time step. For control policy, I'm choosing multi-layer perceptron, but this case with bounds, with hard constraint bounds on its outputs by doing projection. So we have also predefined architectures for these type of transformations. And I'm going to wrap it in the node again. That will be the node for symbolic control policy. That will be mapping measurements of the system states, desired reference trajectories into control actions. And now I have these two nodes, but as opposed to non-cyclic computation graph, I want to do rollout with feedback loops. So for that, we are constructing this system class that is taking list of nodes and is constructing computation graph on these input-output keys. Let me show you how it will look. It will look something like this. I'm expecting my references and initial conditions to come from the dataset. It will be features for control policy that will generate control actions for the model, and I will do rollout of the model over predefined number of steps. That will be the prediction horizon. And this will obtain the state and input trajectories. So this is a true closed loop control problem that now I can differentiate through. So this is exactly the same computational graph what you would use in model priority control. But as opposed to model priority control, we want to learn neural network to solve this offline. Here I am instantiating two variables, my state and reference trajectory, that are really just pointers to the computational graph over there, and creating objective for reference tracking, minimizing state constraints, some terminal state penalty, and putting them all together in a list of objectives and constraints. Here I'm just providing some nice names for a nicer plot. Okay, so I'm going to optimize this closed dynamical system, again with the penalty objective on different loss function terms, and putting everything together in differentiable constraint optimal control problem in this case. How it looks on a high level. Again, very familiar pin architecture. I have samples of the collocation points in my parametric space of the control problem. I have this closed loop system. This node over here is basically this one, the rollout of the policy and system model, which I want to optimize with respect to a range of loss function and objective terms that are aggregated in pin type penalty method loss function. And now I can backpropagate everything to optimize the trainable parameters in here. And using the same API again, standard stochastic gradient descent, exactly the same trainer and the same train method that I used in learning to optimize and PDE training function. So it will converge after some steps, and this cell is just doing a rollout on a test data. Here I am generating some random signals for references and some random initial conditions and observing the rollout. So here I have red are the state trajectories and blue and orange are the states that are tracking the state trajectory. These are the reference. And these are the corresponding control actions. It, for some reason, is too big to show. Oh. Is it better? No. Yeah, still too big. But when I rerun this with new random references and random initial conditions, I have new profiles. And you see, I don't need to recompute the optimization problem because my neural network is already pre-trained, is explicit solution to parametric optimal control problem. So new reference again, and I have now obtained the solution that is orders of magnitude faster than online optimization-based algorithm that typically is implemented in these decision-making schemes. Why it is useful? Every time you have embedded hardware that has a limited memory or limited compute power or limited battery life, you want to reduce the computations as much as possible. And this is the one way how to do that, by pre-computing the solutions offline. Every time when your control problem is too expensive to run in a sampling grade you have. This can be, again, very often in robotics for rapid decision-making in quadcopters, or this is also in power systems when we are solving large-scale economic dispatch or optimal power flow problems, and we have only 5 minutes to solve them. But this decision-making can take hours. So you are restricted to use them only for analytic purposes. But with these physics-informed learning to optimize methods, you can pre-compute the solutions offline and you can go from analytics to real-time decision-making pretty fast. So that's the last example I'm going to show today, but we have way more examples in our open source library. I haven't shown you anything about learning surrogates for ODEs with neural ODEs, universal differential equations, or like coupon operators. Feel free to check it offline. It's exactly the same API that I use for control pins and learning to optimize. With that being said, I want to thank all my wonderful colleagues at PNL and contributors to the library and domain scientists who are driving the development of the tool.
Thank you, Jan. Thank you for your presentation. It's wonderful. George, do you want to?
No, I don't know if Raj is or if Raj or Radha or Leonard want to, library developers, if they want to comment. But it's very impressive. I have some ideas that I will email Jan.
Thank you very much, George. And I'm more than happy to collaborate and make it a community development. That's why we decided to go open source, because we see a lot of potential in interconnecting existing libraries in the PyTorch ecosystem.
Well, I don't know if Jerome is still online.
No,
because
Jerome told me that he has to teach now, so he left.
Okay.
I have a question actually. Oh, sorry.
Oh, Jan,
Raj, please
yeah,
go ahead.
okay. Yeah, Jan, this is Raj from Brown. Just I had a question, like when you use ODE integrator, so it has to go to the loss function, and to differentiate it, like we use like a adjoint method for that. So is it like already implemented, or user has to declare it or customize it for existing ODE?
It is already implemented. We have adjoint method support by actually interfacing with diffeq library written by the original authors of the neural OD paper.
Yes.
We also have our custom OD solvers written in a library that you can unroll and backpropagate through using Autograd.
Okay.
There is a lot of lower hanging fruit for integration. For instance, SD Torch, that's that's the library that we are planning to integrate within a month.
Okay. Also, just last question. So can users specify which mode of AD they want to use, forward or reverse mode?
Yes. Basically, we have integrator that is a wrapper for third-party OD solvers. So when, for instance, the storage diffeq has a range of methods, runge-kuta, trapezoidal, you can specify that as a input parameter to the integrator.
Okay, so like I was asking about in terms of the doing the Jacobian vector and vector Jacobian product. So like for differentiation, because it's PyTorch, I'm not sure if they have implementation for forward mode AD.
Yeah,
they do. They have the func torch.
Okay.
Yeah,
they have this implementation of VGP GVP stuff.
Yes, it's supported in func torch, exactly.
Okay, thank you. So thanks.
Yes.
Raja, that he's asked a question. He just put on the archive a new paper where he abandons backpropagation using only forward passes, actually computing forward derivatives. So that's why I think the question.
Yeah, because it was hard to implement that in the PyTorch for me. Then I used Equinox, the Jax ecosystem.
Yeah.
So the Equinox developer developed another library called Diffrax. So they have like very nice API to convert any user function in the differentiable function. So that's what I used. I kept the paper there. Like I would like to implement that the VJP JVP in this library. So
yeah, we have something similar. We are very much inspired by Patrick Kinger and the team.
Yeah, exactly.
Behind Jax. Unfortunately, the time we started, the Jack was not around. PyTorch was the state-of-the-art library. So we are kind of stuck with it, but I don't think it's a hindrance. There is a great community and a lot of tools developed in PyTorch, and it will be around for a long time. So maybe in a couple of years, or maybe within next year, we may expand and provide backend for Jax. But right now we don't have funding for that. So
yeah, we'll try to find funding for it.
Yeah.
Hi, Jan. Thanks for the very nice talk. This is Jen, also in Crunch Group. So I'm interested in the optimal control part that you just mentioned. So I think my question is like how do you enforce the constraints? Specifically in the case you presented, did you use the projected gradient you mentioned before, or like you use some like different methods there?
The specific problem I showed was the most simple one, just using penalty methods. So there are no constraint satisfaction guarantees. And if you could see in some of these rounds, when the references have been very, very close to the boundary conditions, I was violating the state constraint.
So you use like the soft constraint, right? Like,
exactly, there are soft constraints. Okay. For hard constraints, you would like to use some kind of implicit layers, like projections, to provide you with the correction mechanisms. So we are having a pretty good team at PNL who's doing controls and safety filters, and we have several methods for doing that. The recent trends in control community are so-called control barrier functions or predictive safety filters that allow you to either, for a specific problem, construct some functions that when differentiating provide you with the gradients for correcting your constraints, or for more general problems, solve smaller projection problem after training the neural network when you're deploying a system. So if you're interested more, we can chat. I have a bunch of literature on that topic.
Yeah, thanks. Oh, sorry.
Jen is the one who is trying to do the drone problem. So he had 256 drones in the room trying to cross
calls and at the fastest time, and also without avoiding 256 times to that 512 dimensional problem.
It's yeah, this is a very difficult problem because the one thing is like when the problem has discontinuities or mode changes, it's not as easy to learn it with just sampling because they have degenerate gradients. So for that, some fancier methods and some domain knowledge needs to be exploited. Yeah.
Thanks very much, Jan. That was excellent. I'll follow up with an email.
Thank you very much, George. Thank you very much, everyone, for wonderful questions and engagement. I'm more than happy to receive your feedback. Also, when you have questions or issues with the library, drop it in there. We have quite extensive community support. And as I said, I'll be more than happy for integration with the existing PyTorch SciML ecosystem. Maybe we should create some kind of initiative on that.
Yeah, I will email everybody.
Very good.
Great.
Have a wonderful day. A nice weekend.
Yeah.
Bye-bye.
Drgona, you can close it.
All right, so then it comes to the end of this week's Cron Seminar. Everyone have a good weekend. See you next week. Bye.